Hello everyone, hope you are doing well. Welcome to the online platform Civil Technobricks. Guys, here we will tune for the instantaneous decoding of conceptual knowledge in the field of civil engineering, where study elaborates decoding the earth to build a better world. Today we will go through the core concepts of reservoir induced seismicity and stability of slopes around reservoirs in view of civil engineering. Reservoir-induced seismicity refers to earthquakes that are triggered due to the filling and operation of large reservoirs behind dams. The weight of stored water changes the stress distribution within the Earth's crust and affects nearby rock formations. Water infiltration into fractures and faults increases pore water pressure and reducing the rock strength and stability. So picture second shows that the equal and opposite forces which are acting in the orange color, where the fault plane is there, and through that fault plane n number of cracks are generated to the downstream side of the dam. With reference to this, the whole stability of dam may get disturbed. Slopes around the reservoirs are highly vulnerable because fluctuating water levels alter seepage forces and destabilize soil and rock masses. So civil engineers must have to evaluate geological condition, slope stability, seismic hazards and groundwater behavior before reservoir construction. So earth is not static. It is a system of balanced forces. So we have to balance the forces which are acting on it naturally or with reference to the man-made activities. Defining the reservoir induced seismicity. Short form is that RIS, reservoir induced seismicity. So here lithostatic pressure and hydrological load plus trigger means in natural state the rock are naturally occurred with reference to the lithospheric activity or natural conditions, where n number of forces are acting on it. When that stresses may damage that rock and may it get disturbed with reference to some water contact or with reference to some earthquake vibrations, that is hydrological load or plus triggering activity, then that reservoir induced seismicity comes in picture. So reservoir induced seismicity occurs when reservoir loading disturbs the pre-existing equilibrium of stresses in the earth crust. The natural lithostatic pressure in rocks gets modified after reservoir impoundment. RIS does not create new tectonic stress but activates existing faults and fractures. Hydrological loading due to water infiltration acts as a trigger mechanism for seismic events. Engineers must have to identify the active and inactive fault zones before dam construction. So, the earthquakes triggered by the physical presence of artificial lakes may target the reservoir induced seismicity. So we do not create the tectonic stress. We trigger the release of existing accumulated stress. Just like we are the engineers, so we have to plan the activity to neutralize the stresses. That mechanisms of induced earthquakes. So first is the elastic deformation due to the loading, and second is the fluid diffusion due to the lubricant. The first image which shows the elastic deformation in the rock due to the loading or the pressure or the self weight of the water which is exerted on the rocky layer beneath it. So hydrostatic pressure at the depth balances lithostatic pressure, altering the stress state. In second, fluid diffusion, where lubricating action will be in picture, where the cracks are available within the rock formations, and with respect to that crack, water gets percolated, and at the same time the huge amount of water may also exert the pressure on the horizontal direction or in the vertical direction at the same time. Due to that, there may create n number of other cracks also. So the first mechanism is the elastic deformation, which caused by the additional load of reservoir water. Reservoir loading increases vertical stress within underlying rock strata. Second mechanism is a fluid diffusion where water penetrates faults and joints. Increased pore water reduces effective stress and lowers frictional resistance which along the fault plane. So combined loading and fluid pressure, combining of that loading and fluid pressure may initiate seismic slip along pre-existing faults. The next concept is the pore water pressure, or we can say that pore pressure concept. The pore pressure concept, which is based on the stress. Here the graphical representation, we can say that the normal stress on the x-axis with reference to the shear stress on the y-axis. The effective stress governs the strength and stability of soil and rock masses. Effective stress is calculated as total stress minus pore water pressure. Increase in pore water pressure reduces effective stress and weakens the material. High pore pressure can trigger failure in slopes, foundations, fault planes, fault zones, etc. So monitoring the groundwater pressure is most essential for the dam safety evaluation. So based on the principle of high fluid pressure reduces normal stresses by Hubert and Rube, we have to check the flotation effect also, which is based on the water, that water pushes fault surfaces apart from each other and which reduces the friction in between them. So effective stress is equal to the normal stress minus pore pressure. What are the factors which are influencing on the reservoir induced seismicity? So here the hydrostatic head, pre-existing faults, rate of loading and anisotropy. So these are the four major factors. Rapid reservoir filling increases stress fasterly. Rapid reservoir filling increases stress faster than geological materials can adjust. So greater water depth causes higher hydrostatic pressure on underlying rocks. So pre-existing faults may get critically stressed fractures ready to fail. Pre-existing faults and fractures increase the probability of induced earthquakes. Geological anisotropy influences the direction of stress transfer. Reservoir operation patterns strongly affect seismic response. So hydrostatic head, where the greater depth is equal to the greater pressure at bottom. So the water which is stored in the upstream side of the dam, which acting the huge amount of pressure to the various rock layers which are available below to that dam wall or the catchment area. So the rocks with various faults, folds and fractures or cracks, they must disturb the actual stability or the existing stability. Here the slope stability around reservoirs. Why the stability of slope is most important nearby to the catchment area? Otherwise there will be a landslide in the catchment area and the whole catchment area may get affected due to that siltation or sedimentation. So saturation reduces soil cohesion. Subsequent erosion removes toe support, which results the gravity sliding or hillside creep, or we can say that landslides. So potential slip circle, which is acting the pressure in the orange color towards the various rock layers. At the same time, the rocks are itself acting the resistive force, which is of the friction or cohesion, or we can say that the driving force with reference to the gravity or the weight of gravity or the weight of saturated soil masses. So the reservoir saturation reduces soil suction and weakens slope materials. Increased water content adds weight to slopes and increases driving forces. So pore water pressure decreases shear strength and slope resistance. Subsequent erosion removes the toe support from reservoir slopes and soil stability may lead to landslides, creep and sudden collapse or failures. Here landslides and water level fluctuation. So before and after, see state stable and state critical. In the stable state, the whole water is attached to the rock layer, and in the second state, critically, the forces acting by the water on the rock layer may get erode that embankment, and that mechanism may result in the landslides, or we can say that collapse or fracturing. So when water drops fast, integral pore water pressure remains high. Due to that loss of external support plus heavy saturated soil, it gets failure. So external water supports decreases suddenly during rapid lowering of reservoir level. Rapid drawdown creates dangerous instability conditions. So reservoir slopes may remain stable during steady water conditions. So difference between driving and resisting force may cause the landslides. May cause the landslides. Here, seepage effects and piping effect. So what is meant by piping effect? Piping effect is due to the internal erosion. Water flowing through permeable beds erodes fine material. Lubrication of bedding planes dipping toward the reservoir is a critical failure mode. Seepage occurs when water flows through soil or rock pores. Uncontrolled seepage generates internal erosion within embankments and slopes. Piping develops when fine particles are removed by flowing water or runoff. So continuous erosion creates underground channels and weakens the existing structure of rock. Proper drainage system is most important and essential to control that seepage and piping effect. So monitoring techniques, how we can monitor this by using three phases: seismic phase, deformation phase and hydraulic phase. Seismic monitoring detects earthquake magnitude, frequency and fault orientation. Geodetic monitoring measures surface deformation using GPS and tilt meters. Hydraulic monitoring tracks pore pressure and seepage conditions. Instrumentation provides early warning for instability and seismic activity. Continuous monitoring improves reservoir safety management. Means seismic activity, geodetic activity and hydraulic activity. These three techniques we are used for monitoring that reservoir seismicity. So what are the preventive measures and controls for the same? So the diagram itself suggests that the preventive measures where rock bolting action is there, we have to drill the bolts inside the various rock layers in the exact oblique angle with reference to that wall of the dam. Again, we have to provide the drainage galleries so that whole pipe collects the seepage water from the various bed of the rock layers, and that whole water may be shifted at the outside to the or the downstream side of the dam. At the same time, grouting curtains are also provided or constructed exact below to that wall of the dam, which provides the stability and enhance the strength of the existing rocks. So control impoundment means slow filling rates to allow stress accommodation within the dam and surrounding rock mass. What is meant by slope stabilization? The mechanical retention through the installation of rock bolts and ground anchors to increase shear strength. And what is meant by the drainage? Provided reducing pore pressure to increase effective friction and improve overall cohesive strength, mitigating instability risk. These are all the preventive measures and controls which are provided by the engineers for the maintaining the life of the dam. What are the geological investigations? Fault mapping, lithological characteristic study and permeability effect. The permeability is the testing of basin floor. Lithological characteristics are by spotting the incompetent beds or the lower strength beds, just like shale rocks or muddy nature. Fault mapping is the identifying active versus inactive fractures. So geological investigation identify active faults and weak zones. Lithological studies determine rock strength and permeability. Geophysical methods which helps to detect hidden subsurface discontinuities. Permeability testing evaluates groundwater movement characteristics. So pre-impoundment investigation is essential for safe reservoir planning. So prevention starts with mapping geophysical methods like seismic reflection, gravity, which reveal hidden hazards before the water rises. Next, Environmental and geomorphic impacts. Here the sediment we have to trap. Sediment trapping. At the initial basin, V shape. At second part, sediment deposition. That V shape is minimized due to that sedimentation part. And three is the compaction and trapping, where the large amount of valley captured by that sediment. So sediment trap is the reservoir after basin geometry via deposition. Erosion is the shoreline alteration and downstream starvation. Megabasics are the large scale landslides, debris, fields. So reservoirs alter natural sediment transportation process. Sediment deposition changes the basin morphology over the time. Reservoir loading may cause compaction and land deformation. Erosion patterns around slopes and shorelines become modified. Large scale landslides may occur due to the geomorphic changes. What are the risk mitigation strategies required? So we have to plan from zoning, seismic design and emergency action. Zoning, which were restricting downstream development. Seismic design, which is based on the flexible cores of dams in reservoir induced seismicity zones. Emergency action plans for the triggered by real time monitoring. Real time monitoring systems provide early warning against instability. Threshold based apart systems, or we can say that the threshold checks help manage emergency situations. Controlled reservoir operation minimizes seismic and slopes risk. Land use zoning restricts unsafe development near reservoirs. Emergency action plans improve disaster preparedness and public safety. So with reference to that risk mitigation strategies and environmental geomorphic impacts, we can sustain our rock, or we can develop the strength in between the various rock layers by using some preventive measures just like rock bolting. We can maintain the existing life of the reservoir, and we can minimize the reservoir induced seismicity effect. Stay tuned guys, happy learning.